Hello, I'm matt.ballance, and I'm here to talk about PyVSC, a Python library for doing SystemVerilog-style constraints and coverage in Python. In this presentation, we'll talk about the background, motivation, and goals for the PyVSC library. We'll talk about how data and constraints are captured using the library to do constrained random stimulus generation. We'll talk about how functional coverage is defined, collected, and used in the PyVSC library. We'll also talk about how PyVSC integrates into an environment. And finally, we'll talk about the future of the library. Randomized data and functional coverage are heavily used for functional verification. This has been a very primary methodology driven by a couple of languages, but most recently primarily SystemVerilog. This is heavily used with the UVM library, Universal Verification Methodology. It's a very standard practice in industry today. Using randomized stimulus and coverage is very useful outside of simulation-based verification as well. And oftentimes we either see dedicated libraries used for this purpose, or sometimes users will leverage the capabilities of their simulation-based environment, SystemVerilog, as a way to get these capabilities. PyVSC is a Python package that provides these capabilities. PyVSC stands for Python Verification, Stimulus, and Coverage. The key goals of the PyVSC library are really to bring the SystemVerilog look and feel to Python constraints and functional coverage. So in other words, have as similar a look and feel as possible to SystemVerilog, as similar as possible a feature set to what SystemVerilog provides. And this is because there are many users that are very familiar with these capabilities from SystemVerilog, as these users may be looking to leverage Python as part of their verification. It makes it much easier to adopt a capability that aligns with the familiar features that come from SystemVerilog. Now, when it comes to performance and capacity, the goal here also is to have very similar performance and capacity characteristics to what SystemVerilog environments provide today. And finally, it's very important to be able to take forward the coverage data, the functional coverage data that's captured from a library like this, and make use of it outside of the Python environment. PyVSC addresses all of these three goals, and we'll look at how across the next few slides. Okay, next let's see how we capture constraints and randomized data using the PyVSC library. So with PyVSC, we use decorators, which are these Python things with the little @ symbol, ampersand symbol, to identify key types within the description. In this case, @VSC randobj identifies a class as being randomizable. This decorator will cause PyVSC to build mechanisms, infrastructure into the class such that fields can be randomized, constraints are recognized, so on and so forth. The reason for using a decorator in this case is that it makes it possible to layer randomization onto an existing class hierarchy without mucking with the inheritance hierarchy. So the PyVSC library provides specific data types to be used in constraints. This is partially because of the mechanisms of an embedded domain-specific language, but it's also because when you are randomizing data for functional verification, it's very important to be able to specify what the width of that data is. So in this example over here, we're creating two fields. Each of them are 8 bits wide. One directly specifies that it's a rand bit, 8 bits wide. The other uses a convenience type, which might be more familiar to C++ programmers, uint8 under T. So PyVSC as a library supports scalar fields, enum type fields, class type fields, arrays and lists. And a class like this, a randobj decorated class, supports the randomization hooks that you might be used to from SystemVerilog. Methods that are called before randomization begins and after it's complete, so that you can do setup, initialization, and post-computation. Constraints with PyVSC are captured within methods, but these methods need to be decorated with a constraint decorator. Now, when you look at the code here, it looks almost the same as a regular if-then-else statement. But recognize that what's inside this method, this is an aspect of the embedded domain-specific language. This code will not be executed procedurally. It will be executed once to build a declarative constraint that will later be solved as part of the randomization process. So when you're writing constraints with PyVSC, you need to be very aware of how these functions, how these constraint methods are going to be evaluated. They'll be run once, and so while it's possible to put some procedural constructs in there, you need to be aware of how those constructs will be evaluated. So in this case, we have an if-then-else that just checks the value of one variable, constrains another variable based on that value. Now, just as in SystemVerilog, constraints support inheritance. And if you're an object-oriented programmer, you can think of constraints in this sense as being virtual, like virtual methods. So in the example that we have here, we have a base class that defines a constraint named AB_C. It has the constraint A is less than B. Now we create a derived class, my extended S, that derives from my base. In this case, we also have a constraint named AB_C. Now, in Python, in object-oriented languages, you would expect a method in this case. If we have an instance of myXS and we call ABC, you would expect this method, the one in the derived class, to be called because it's virtual. The same happens in this case with constraints, where if we have an instance of myX_S, the constraint A greater than B holds. If we have an instance of my base S, the constraint A less than B holds. So this again is just another area where we align with SystemVerilog semantics. Now, in order to randomize a class with PyVSC, we have two methods that we can call. We have a plain randomize method, and this is present on every randobj decorated class. We also have a randomize with method that we can use to add in specific constraints. So in this case, we're using that randomize with method as a way to constrain the A rand variable here to be the same as a loop index within our procedural loop. So every time through the loop, we'll constrain the A variable to be equal to the index. The B variable will be randomized to match. So here again, similar characteristics to what you would be used to in SystemVerilog. Now, PyVSC actually has very good coverage for the SystemVerilog constraint features and the SystemVerilog-Style data types. Here's sort of a summary of the feature support. This makes it very easy for a user that's knowledgeable in SystemVerilog to pick up the feature set and make use of it in much the same way that they're used to using SystemVerilog. I'll talk a bit more about this at the end of the presentation, but the future I really see here going forward is to go beyond the capabilities of SystemVerilog. Python provides much more capabilities in terms of dynamic building of constructs and adaptation on the fly. And I see a fair amount of space to explore here, going beyond the fundamental features that users are used to with functional verification and constraints. All right, let's talk about how we capture functional coverage using the PyVSC library. A cover group with the PyVSC library is described in much the same way that a randomized class is, in this case with a cover group decorator. The init method for a cover group class specifies both how data will be sampled, how we'll get data into the cover group, as well as the cover points and crosses that we'll use to collect metrics on that data. Sampling data for a given cover group instance happens when we call the sample method on an instance of a cover group class. So let's look at the two ways that we can get data into a class for sampling. The first approach is to actually specify to the PyVSC library what the parameters will be to the sample method. And we do that by calling this withSample method, which is very similar if you're from SystemVerilog background as the withSample function or with function sample mechanism that SystemVerilog provides. In this case, we specify that the sample method will have one parameter. It will be named A, and the type will be 4-bit field. Now, through some Python magic, this field A is made a class member, and so we can define our cover point on this A variable. We've got some bins here, we've got a cover point, and then when we want to sample some data, we pass it explicitly to the sample method. So the value 1 will be sampled by this cover point, the value 2 will be sampled by this cover point. So this works pretty well for passing small amounts of data. And the restriction really here is that the parameters of the sample method need to be PyVSC data types, either primitives, as is shown here, or random objects, in order for PyVSC to work correctly. The second method is a bit more abstract. This works well in more complex situations where the data being sampled really isn't PyVSC data. And the approach used here is to actually give the cover point a Python lambda expression as its target. So a lambda expression is a callable object that returns a value. In this case, it's going to evaluate the object.a reference within this class, and whatever the object is currently pointing to, it's going to return the A field. This is nice because, first off, notice that my object here is not a PyVSC object. There's no decorator. Secondly, initially, I have no idea what the object is. And over time, as I sample my data, I'm going to get different objects that I want to have sampled. So the mechanism here is, okay, I have my object coming in. Maybe this is from some listener from some stream of data. I set the obj field in my cover group to the object instance that I want to sample. I call sample, and when the cover point is sampled, this lambda expression will be evaluated. It will get whatever the current value of A is, and everything's good from here on. So this works well in more complex situations. Now, the coverage features that PyVSC supports are a bit more limited, or a bit more of a subset of the SystemVerilog constructs compared to the constraint constructs. We have the fundamentals covered in terms of cover point types, cover point instances, or cover group types and instances, basic bins, arrays of bins, single bins. Some of the more detailed constructs, transition bins, for example, some of the exclusion bins on cover point crosses, these are not yet supported, and those are planned in the future. If you have certain constructs that are very important to you, feel free to raise an issue on GitHub where we support the project, and I'll be happy to look at priorities to make sure that the most important features get supported first. Okay, let's talk a bit about how PyVSC fits into a test bench environment. PyVSC is a Python library, and in this sense, it's very nice and flexible in fitting into pretty much any environment you could think of. On the plus side, this is good, very flexible, lots of opportunities. On the negative side, this means that you as a user of PyVSC are on the hook for a little bit more work. You don't automatically get this supported just by using some other library. Good news, though, there really are two integration points only for PyVSC. There is the random seed that controls the specific results that PyVSC supports with randomization. And then there's the process of saving coverage data. These are really the primary integration points between the library and any given environment. So PyVSC uses the Python random package as a way to get its random seed. Basically, if you use the same seed, you should get the same random results when you randomize data over time. If you change the seed, ideally you would get a different set of results. So depending on the environment that you're plugging into, it might make sense to directly specify the seed. In this case, we're setting the master global seed in the Python random package to 0. If you're using another environment such as CocoaDB, many of these automatically configure the random package with the master seed automatically. CocoaDB, for example, does do that via a variety of mechanisms, environment variables and command line options. So if you're using one of these environments, this aspect of integration is taken care of. The second aspect of integration is how we get coverage data out of the PyVSC library. We have two mechanisms for producing simple text-like reports. One is the actual coverage report method, and this prints either to the console or to a file a simple coverage report that looks like this. It's hierarchical, and it specifies the level of coverage achieved on the cover group types and instances that are defined. There's also a get coverage report model method that returns a Python object that has a similar structure to this that you could use to create custom reports. The second and perhaps even more interesting mechanism for getting coverage out is to write a coverage database. This saves the coverage in a UCIS XML file. UCIS stands for Universal Coverage Interchange Specification. It's an Accelera standard. And by saving the coverage in this format, we're able to take it outside the tool, perhaps process it with some other tools. One thing that we can do with it is to view it graphically. There's a little viewer, PyUCIS viewer on GitHub that you can use to look at your coverage in a graphical manner like this. So if you're integrating PyVSC into your environment and you want to look at coverage, you'll want to make sure that you call the right coverage DB method before your environment exits. Okay, let's look at one example of how PyVSC is being used today, and that's the Google Risk VDV package. So the Risk VDV project, if you're familiar with it or not, generates test programs for RISC-V cores. It uses constrained random generation to generate test programs, assembly programs. The package defines coverage metrics for metrics to collect about the instructions and machine state based on execution of those tests. This package provides and has provided for quite some time a SystemVerilog constraint and functional coverage-based description for generating these programs and capturing the functional coverage. Now, the package also provides a Python-based generator that uses PyVSC for randomization and coverage collection. If you're interested in looking at this, you can find this on GitHub too, with instructions on how to generate test programs. So the way that this works in terms of a process, the instruction stream generator runs, and this produces a whole series of test programs. Might be 10,000, might be 100,000. These programs run either through an instruction set simulator or through simulation on an RTL model, and they produce a set of execution trace files that are then sampled by the functional coverage model. So what we're really looking for here is specific instructions being executed, specific register states being occurring due to the execution of those instructions. And so finally, at the end, we get a set of coverage metrics on what happened when the random test programs that we generated executed against a model of a Risk V processor. So the way that PyVSC is integrated into this process is at the beginning, at the end. PyVSC in the Python flow is used for random data generation. It's, the constraints and random data generation drive generation of that instruction stream. And at the end of the flow, PyVSC cover groups are used to sample metrics from the execution trace files, metrics about what happened as the instruction stream executed. So from a Python perspective, the Python generator, just a few metrics I thought might be interesting here about how PyVSC is used in this case. The Python generator is around 8,000 lines of code overall. And I didn't make any attempt really to break that down in terms of how many lines are constraints versus how much is procedural code using the random data. It's going to be a mix. In terms of the functional coverage being collected, there are around on the order of 50 cover groups containing an aggregate of 300 cover points and crosses. So the description here is relatively sizable already, which should give you a sense of the capacity and complexity that PyVSC can handle. Okay, so talking a bit about where we're going with PyVSC. The plan really includes a few things. I mentioned that there is work ongoing to flesh out the rest of the SystemVerilog constructs that are not yet present, primarily in the space of functional coverage collection. We're looking at things beyond SystemVerilog capabilities in terms of the ability to programmatically and dynamically define and change constraints in coverage, as well as exploring some additional features perhaps for steering stimulus in user-defined directions in more flexible, usable ways perhaps than SystemVerilog supports. On the performance side, we are looking at a project to redo a little bit some of the infrastructure under the embedded domain-specific language for performance reasons. Python is a great language for integration, and right now, we have an SMT solver boolector integrated under the hood, but some of that glue logic even is starting to get a little bit slow when it's written in pure Python. So we're looking at re-implementing some of the guts of that algorithm in C++ for performance reasons. Finally, we're looking at specific environment integrations. Can we make, for example, in CocoaDB, is there a way that we can ensure that functional coverage gets saved automatically so the user doesn't have to worry about that? So if you're interested in getting started with PyVSC, one of the easiest things to start with is the documentation on PyVSC readthedocs.io. PyVSC is provided as a pre-built package on the PyPy platform. So simply running pip install PyVSC will get you the package and the required dependencies. Currently, this is supported for Linux and Mac OS. At the moment, there's no Windows support, but that is also something that's being looked at. If you find issues, if you have questions, if you have suggestions, come find us on GitHub. You can find the source code there. You can find issue trackers. That's the best place to interact. So thank you for taking the time to learn a little bit more about PyVSC. I hope you found it useful, and I hope you have some new ideas now on ways you can make use of constraints, randomized data, and functional coverage in Python. Thank you.